Hi everyone, I am Bhargav. In this video we are going to discuss about multiple correct type questions in the assignment 2. The first question is, we are given a quantum state 1 by square root 2 times qubit 0 minus qubit 1. As in solving one of the questions in single type correct answer, we have written a state in form cos theta by 2 0 plus e power I phi to locate a state on a Bloch sphere. We write a quantum state in this form. By comparing the coefficients here, we see that cos theta by 2 is 1 by root 2, and we can see that e power I phi is minus 1 and sin theta by 2 is 1 by square root 2. From these two we can say that theta by 2 is 45 degrees, and from this we see that phi is 180 degrees. So we obtain phi as 180 degrees and theta as 90 degrees. So now we look at the options. Option A says theta is equal to phi by 2, and the relation is true indeed, because 90 degrees is same as 180 degree divided by 2. And the next option says theta equal to phi, which is wrong, and we have theta as 90 degrees, that is angle made by vector with z axis is 90 degrees. So the state should be lying in equatorial plane, because if we see this, say this is equatorial plane where the axis is x, y and this is z, and any state which is making 90 degrees with the z axis should be lying in equatorial plane. So the quantum state should be lying in equatorial plane considering the Bloch sphere. So the answers to this question are A, which says theta is phi by 2, and which also says the state lies in equatorial plane. Question 2 is about superdense coding, where a single qubit is communicated in place of two classical bits. And here is the question: while processing a quantum state sent to Bob from Alice, here Alice intends to communicate classical bits 1 and 1, and they share a Bell state 0 0 plus 1 1 by root 2. Which of the following states Bob would encounter at different stages of processing? And now the first stage of processing is applying this gate, which is which is 1 0 0 1, this 1 multiplied by this matrix, and now the 0 multiplied by this matrix, and 0 multiplied by this matrix, and minus 1 multiplied by the matrix. And now this gate is applied on the Bell state they share. The Bell state they share is which is equal to the vector 1 by square root 2 1 0 0 1. We need to get fluent with the vector forms of these qubits to do these problems efficiently. And now this matrix is multiplied with this vector, and the output or the resultant is 1 by square root 2. The first row multiplied with the column gives a 1. The second row multiplied with the vector gives 0. Similarly, the third row also gives 0. But the fourth row gives -1. We can see that this can be written as 1 by square root 2 times 1000 minus 0001, which is 1 by square root 2 times this is 00 state and this is 11 state. After the first stage of processing, he has 1 by square root 2 qubit 00 minus qubit 11, and after that a C0 gate is applied where first qubit is control bit and second is target bit. And the output is, as first bit is control bit and first bit is 0, the second bit doesn't get altered, and in this next state where we have control bit as 1, second qubit gets flipped, that is 1 0, and this state can be written as so the output is and then Hadamard gate is applied on qubit 1. We know that on applying Hadamard gate on 0, we obtain this state, and when Hadamard gate applied on qubit 1, we obtains. So based on these two results, when Hadamard gate is applied on this state, the qubit 0 transforms to this state and qubit 1 transforms to this state. So effectively applying Hadamard gate on this state is subtracting these two from each other and multiplying with 1 by square root 2 term. So which gives us, on subtracting these two terms, we obtain qubit 1 divided by square root 2 times, so we write this down, we obtain 1 by square root 2 times applying Hadamard gate on the first qubit gives, on the second qubit it gives times qubit 0. So the final state, is 1 by square root 2 times the qubit 0 gets cancelled and qubit 1 gets multiplied with 2 with a factor of square root 2 from the initial terms, which is equal to, and we see that all the coefficients get cancelled and we obtain 1 0. And the question asks about what are the states Bob would encounter at different stages of processing. In the different stages of processing, we obtain qubit 1 0, and the previous calculation we have also got this qubit, and now we look at each of the options and try to decide whether we have seen the state in any different stage of processing. So the first option says 1 1. We never obtain any state 1 1 as output, and option B 1 0. The final output which we obtain is 1 0. So option B is correct. And option C 1 by square root 2 qubit 0 0 minus qubit 1 0. After applying C naught gate, we obtain that state 1 by square root 2 0 0 minus 1 0, and the option D is just another way of writing option C by taking the qubit 0 to the right hand side, which is written here. So the correct options to this problem are B, C and D, which are the quantum states obtained by Bob at different stages of processing. And now we look at question 3. Question 3 asks to find which of the following operator relations for the quantum gates are true, and we go by option wise. Option A says that square of C naught square gate is identity matrix of size 4 cross 4. A C naught gate can have two forms, where the first qubit can act as control bit or second qubit can act as control bit. Suppose the first bit is the control bit, then C naught gate is of form these are mentioned in lecture. C naught square is where we multiply this matrix with itself, and now when we multiply this matrix again with itself, we multiply the first row with the first column, where we obtain 1, and when we multiply first row with second column, we obtain 0. Similarly in the second case, and when we multiply the third row with the columns, we obtain 1 only when we multiply the third row with the third column. Similarly for the fourth row, we see that we obtain identity matrix of size 4 cross 4. Similarly, when we multiply CC naught square with CC naught gate with itself, we obtain identity matrix of size 8 cross 8. So option A is correct and option B is wrong. And now we look at X gate. X gate is 0 1 1 0, and X square is 0 1 1 0 times the same matrix, which gives, when the first row multiplied with first column, we obtain 1. The first row multiplied with second column gives 0, and similarly other elements. We see that X square is indeed identity matrix of size 2 cross 2. So option C is also correct. And coming to option D, we have Z equal to 1 0 0 minus 1, and Z square is multiplying Z matrix with itself. We obtain, by multiplying first row and first column, we obtain 1. By multiplying first row with second column, we obtain 0. And multiplying second row with second column, we obtain 1, which is also identity matrix. But the option says Z square is equal to Z. So the option is incorrect. So the correct options in this problem are only A, which says C naught square is an identity matrix of size 4 cross 4, and option C, which says X square is a matrix which is identity with size 2 cross 2. Question 4 asks us to verify which of the following relations are true. We are given 4 different relations and we need to verify which of them are correct. And we go option by option. In the question 4, option A says that H X H is Z. We know that H matrix is 1 by square root 2, 1, 1, 1 minus 1, and X is 0, 1, 1, 0, and again H is 1, 1, 1 minus 1, square root 2. When we multiply these matrices, we multiply these factors, it counts to 1 by 2, and then multiply H and X, we obtain 1, 1 minus 1, 1. When we multiply with H, we obtain 2, 0, 0 minus 2, which is 1, 0, 0 minus 1, which is indeed Z. So option A is correct. Similarly, we verify each of the other options. For example, let's verify D. X, Z, X is equal to Z. X is 0, 1, 1, 0, and Z is 1, 0, 0 minus 1, and X is 0, 1, 1, 0. Multiplying first two matrices, we obtain 0, minus 1, 1, 0. And multiplying these two matrices, we obtain minus 1, 0, 0, and 1, which is minus of 1, 0, 0 minus 1, which is minus Z gate. But the option says it is equal to Z, but we obtain it is equal to minus Z. So this option is incorrect. Similarly, verifying other two options which are B and C, we see that C is correct and B is incorrect. So the correct options to this question are A and C. Before going to solve these questions, we try to look at definitions of unitary matrix, Hermitian matrix, and normal matrix. A matrix is called unitary when it satisfies the relation A times A star is equal to I. A star is a matrix obtained by replacing the terms in matrix A with their complex conjugates and applying a transpose. And the matrix is called Hermitian when it satisfies A equal to A star. The matrix is called normal when it satisfies relation A star is equal to A star A. These are the definitions of these three terms: unitary matrix, Hermitian matrix, and normal matrix. And now we look at questions 5 and 6. Question 5. We are given matrix 1 by 2 times 1 minus I 1 plus I, and we are asked to verify whether this matrix is unitary or not, or Hermitian or normal. And we first try to compute. Let us denote this matrix with A, and let us compute A star. A star is replacing the terms in A with their complex conjugates and taking transpose of it. Transpose is interchanging rows with columns. The first row is 1 minus I and 1 plus I. So the first column should be 1 minus I and 1 plus I. Similarly, the second column should be the second row of the previous matrix. As this matrix is symmetric matrix, we don't see any change between final matrix and its transpose. And let us compute A times A star. We multiply scalars, so we obtain 1 by 4. And now we multiply the first row with the first column. where we have 1 minus I square plus 1 minus I square. 1 plus I multiplied with 1 minus I gives 1 minus I square, and 1 minus I multiplied with 1 plus I gives 1 minus I square. And the second term is 1 plus I multiplied with 1 plus I. Similarly, 1 minus I multiplied with 1 minus I. The third term is and now we see that I square is minus 1 and minus I square is 1. So we have 1 plus 1 plus 1 plus 1, 4, and adding these two, 1 plus I whole square is 1 plus I square plus 2I. 1 plus I square is identical to 0. So we obtain 2I from this term, and similarly we obtain minus 2I from this term. They both get cancelled and we obtain 0. Similarly, this term equals to 0 and this term equals to 4. So we obtain identity matrix. And now we see that A into A star is I. So the given matrix is unitary. And now to verify whether it is Hermitian or not, we observe that A has the first term 1 plus I, but A star has first term 1 minus I. So A is not equal to A star. So not Hermitian. And as you see that A times A star is I, that is A star is inverse of A. So we can write it as A star is inverse of A, and we know that multiplying A inverse with A or A with A inverse gives the same identity matrix. We can write that as A times A star equal to I. So now we see that A times A star is equal to A star A, because we already know that A star is A inverse. Multiplying these two matrices in any order will give us identity matrix. So now using this relation we can confirm that matrix A is normal. So the given last one. So we see that the given matrix is unitary but not Hermitian and also normal. So the correct options for this question are A and C. And we come to the last question of assignment, question 6. Question 6 is about Hadamard gate. What are the properties of Hadamard gate? We see that H is 1 by square root 2 times 1, 1, 1 minus 1. And now to verify whether it is Hermitian or not, we compute H star. H star is replacing original terms in H with their complex conjugate. As all the terms are real, we obtain the same matrix, and we need to take transpose. After taking transpose, we end up with same matrix again. And now we can clearly see that H is equal to H star. So it is Hermitian. And to verify whether it is unitary or not, let us multiply H with H star. That is, first multiply the scalars, we obtain 1 by 2, and multiplying first row with the first column, we obtain 2, and the first row with the second column, we get 0 and 0 and 2. We obtain identity matrix. So H is also unitary. And the option C is, it is self inverse, that is H minus is, that is H inverse is equal to H. We see that as we obtained that H times H star is I, H star is equal to H inverse, but H star is also equal to H. So we have relation H is equal to H inverse. So it is self inverse. And option D says that acting on an arbitrary state, it preserves the norm of the state vector. To verify this, let us take an arbitrary state A, B. Now applying, let us take an arbitrary state A, B. Norm of this vector is square root A square plus B square. And now after applying Hadamard gate on this state A, B, we obtain A plus B and A minus B, and norm of this vector is A plus B divided by root 2 square plus A minus B divided by root 2 square and whole square root, which is equal to A square plus B square plus 2AB by 2 plus A square plus B square minus 2AB divided by 2, that is equal to 2AB term gets cancelled and A square plus B square by 2 is multiplied with 2, and we finally obtain A square plus B square. So we see that norm of this vector doesn't get altered even when it applied with Hadamard gate. So option D is also true, which states that acting on an arbitrary gate, it preserves the norm of the state vector. So we have all the options is correct. A, B, C, D, all the options are correct. And now concluding this assignment, in this assignment we have solved many problems related to quantum gates and representing a qubit in a Bloch sphere and dealing with these quantum gates X, Y, Z. We note that X gate is also same as a NOT gate, and we have seen several properties of Hadamard gate, and we have also understood the definitions of Hermitian matrix, unitary matrix, self-inverse and normal matrix, and we have also verified certain properties of these gates such as X, ZX is equal to minus Z and several others. And we have also solved some problems on superdense coding and quantum teleportation, where we have seen what are the processing done by Alice and Bob to get a qubit teleported, and in superdense coding we have also seen the concept where single qubit is sent in place of 2 classical bits, and we have also dealt with some quantum circuits. So here we end this assignment.